the waveguides, and we have found a general expression for, sorry, just a second. Okay, so in the last class we had looked at the different modes. We saw that if there is no component of electric and magnetic field along the direction of propagation, then there will not be a wave inside rectangular waveguide. Similarly, we have looked at TE mode, TM mode, and hybrid mode. And then we had derived an expression for EZS, which is coming in our equations for EXS, EYS, HXS, HYS. There is coming, we are EZS and HZS is coming, and we have found a general expression like this. And next we are going to look at specifically the TM mode. Okay, so in TM mode, transverse magnetic means the magnetic component will always be perpendicular to the direction of propagation. So our magnetic component is HZ, the direction of propagation is Z. So the component of magnetic field along the direction of propagation will be 0. But for transverse magnetic mode, there will be a component along direction of propagation, which is the electric field. So electric field component will be there along the direction of propagation, but magnetic field component will be 0. So we have the rectangular waveguide like this. This is a 2D figure, and the length is A along X, and length is B along Y. And the waveguide is made up of a metal which has sigma C is equal to infinity, and the electric field in that metal will be 0. So at this boundary of metal and a dielectric, the electric field is 0. That is a very important point, because we are making use of that boundary condition to find out the exact solution for our EZS and HZS. Okay, so let us start. Okay, so what do you mean by at this metallic? Let me write that at dielectric metal or conductor boundary. This we have already seen that either you can assume or you can argue that in a metal the electric field is 0, or you have the conductor interface where there won't be any electric field. So in this case, at dielectric metal boundary, only on those boundaries, okay, the value of Ez is 0. That means EZS is equal to 0 at Y equal to 0, because that is this position. EZS is equal to 0 at Y equal to B. EZS is equal to 0 at X equal to 0, and EZS is equal to 0 at X equal to A. So these are the boundary conditions. Actually, in fact, instead of specifying that at Y equal to 0, you can say that at this boundary for all y between 0 and b, the electric field component is 0. Okay, or at this side for all x between 0 and a, the electric field component is 0. Similarly, at all x between, so at all y between 0 and b at x equal to a, the component is 0. At all x between 0 and a at y equal to b, the component is 0. You can do that also for all x and y. Okay, but the electric field component is 0 only in these boundaries. That you should be careful. There is still electric field component inside the dielectric. Okay, because if there is no electric field component inside the dielectric, the wave will not exist because already Hz is 0. Okay, so that you should be careful. Fine. Now we will apply this conditions, which is boundary conditions. Let me number this as, let's say, 1, 2, 3, and 4. Okay, so we are going to apply the boundary condition to the equation, this one. Let me number this as A. Let me number this as B. Okay, so we are going to apply the boundary conditions to the equations A and B. We'll apply it to A and B similar one. Okay, so let's apply the first boundary condition. Applying 1 in A implies Ez is equal to 0 at y equal to 0. So our equation of A is this. Let me write this again so that we can just modify the equation directly. Okay, so if you substitute y is equal to 0, so there is y equal to 0 here. Let me substitute this here and here. So when you substitute y is equal to 0, you see, and you say the value of Ez is equal to 0, which means this value is equal to 0 at y equal to 0. So I can write 0 is equal to C1 cos, or let me do it in a bit more easier way. Let me multiply this C6 with all these terms. So I can write this as A1 cos kxx plus A2 sin kxx multiplied by A3 cos kyy plus A4 sin kyy into e raised to minus gamma z, where A1 is actually C1 into C6, A2 is C2 into C6, A3 is C3 into C6, and A4 is C4 into C6. I just multiply this constant C6 with all these constants. That's all. So I renamed it as A1. Now, at y equal to 0 means you need to substitute here is equal to 0, and this is also equal to 0. So this is A1 cos kxx plus A2 sin kxx multiplied by cos 0 is 1. Okay, so you will have A3. So this is multiplied by A3 plus sine 0 is 0. So this is 0. So I have our equation 0 is equal to A3 multiplied by A1 cos kxx plus A2 sin kxx. Now you need to find out what is the condition under which this equation will become 0, because the left hand side is 0. Okay, now you see that this part is actually a sum of cos and sine terms. Okay, now the sum of these terms cannot be 0 for all x. Let me write that also for you. For all x. That means at this boundary condition, whatever be the value of x, you should have the left hand side equal to 0, which cannot be possible with this in this term. So only possibility in which this is equal to 0 is when A3 is equal to 0. Okay. So the argument is like this. This is sum of cos and sine terms multiplied by constants. It can only be 0 if A1 and A2 is 0, which is highly unlikely. So the other possibility is when A3 is equal to 0. So the only possibility here for this equation to become 0 is when the constant A3 is equal to 0. So our first result is the value of A3 is 0. Okay. So the equation A now will become A1 cos kxx plus A2 sin kxx multiplied by A4 sin kyy because A3 is 0. Okay, let me write this as equation A1. Now let's apply boundary condition 2, or to make it more simpler, let me apply the boundary condition 3 because that is with the 0, x equal to 0. Okay, that is EZX is equal to 0 at x equal to 0. We are applying this boundary condition in A1. So this is actually EZS. So when you apply this boundary condition, so you say 0 is equal to A1 cos 0. When you substitute 0 here, so when you substitute x equal to 0, this is cos 0. Cos 0 is 1. Plus, when you substitute 0 here, this is sine 0, which means this is 0, multiplied by A4 sine ky y. So this should be 0 for all y. Okay. Now, you see that y ranges from 0 to b in this case. So when y ranges from 0 to b, the sine value will not be 0 from 0 to b, because you will have 0, 1, 1 by 2, 1 by root 2, etc. So this term is not 0. Now, other possibility is A4 is 0. So when A4 is 0, if you look at this equation, the complete equation, A3 is already 0. Now A4 is, if A4 is also 0, then this equation, this whole equation will be 0 for all x and y, which is not possible because you need to have EZX. Okay, so let me write that argument. So A3 is equal to 0. This is already proved. Okay, so let me write this as equation number, let me mark as 1. For 1 to be 0, the possibilities are like this. 1, sine ky into y is equal to 0. Not possible. Why? Because as y varies, sine ky has non-zero values. So this should be 0 for all y, which is not possible. Let me write for all y. Second possibility, A4 is equal to 0. But if A4 is equal to 0, implies equation A is equal to 0, that is EZS is equal to 0 for all x and y. Not possible, because you need to have some value of EZS inside the waveguide. Only on that boundary you need to have the value is equal to 0. Okay. So if you substitute this A4 is equal to 0 in the A equation, since A3 is equal to 0, this EZ will always be 0. So only possibility is A1 is equal to 0. This is condition number 2. Okay, so we have proved two conditions, A1 is equal to 0 and A3 is equal to 0. So substituting condition 2 in A1 implies EZS is equal to, now see A1 is equal to 0. So now we will be left with only two terms, which is this and this, because this is already 0, A1 is 0. So you will have A1, A4 sine kxx into sine kyy into, I think I forgot to multiply it with e raised to minus gamma z. Like that also. This is multiplied by e raised to minus gamma z into e raised to minus gamma z. Okay, so let me rename A1 into A4 as E0. Okay, so this is equal to E0 sine kxx sine kyy e raised to minus gamma z. Okay, so in all these terms, you will have e raised to minus gamma z. Now, e raised to minus gamma z will be 0 only when z equal to infinity. Okay, so this is 0 only if z equal to infinity, which is not possible. Okay, because the wave is traveling from z equal to some value to z equal to some value, so it can have any value of z. Okay. Now, let us apply the next few conditions. So let me number this as A2. Sorry, I think that should be, yeah, A2. Applying condition number 2 in A2, which means EZS is equal to 0 at y equal to b. So I can write 0 is equal to E0 sine kxx sine ky. The value of y will now be b e raised to minus gamma z. Okay, so here you have substituted y equal to b. Okay, now for this equation to be 0, you see this cannot be 0 because it can, z cannot be always infinity. Now E0 is some constant. Okay, so only possibility, so if I make A1 or A4 equal to 0, because E0, I can make E0 is equal to 0. But when you make E0 is equal to 0, the complete equation will become 0. Okay, for example, E0 is product of A1 and A4. A2 is already 0, A3 is already 0. If I make A1 equal to 0, this term will completely be 0 for all x and y, which means EZS will always be 0, which is not possible. If I make A4 is equal to 0, this complete term will always be 0, which is not possible because Ez is not equal to 0 for inside the dielectric. So the only possibility for this, the only possibility is when sine kxx is equal to 0. Sorry, because you cannot make sine kx equal to 0 because x is varying here. So for all x, it cannot be 0 because sine kx will have some value. So only possibility is when sine ky b is equal to 0. So when will this be 0? Because b is a constant. So only whenever the sine term is a multiple of pi, sine is 0. For example, sine pi is equal to 0, sine 2 pi is equal to 0, sine 3 pi is equal to 0, or in general, sine m pi is equal to 0, where m can be 1, 2, 3, etc. So for this to be 0 implies the ky into b should be a integral multiple of pi, where m equal to 1, 2, 3. Okay, let me rename this as n. N is some integer value, just to follow the convention. Okay, so which means the ky should be n pi by b. This is a very important result. Okay, fine. Now let's apply condition number 4 in A2. That is, EZS is equal to 0 at x equal to a. So I can write 0 is equal to E0 sine kxa sine ky y e raised to minus gamma z. Now this equal to 0 is the only possibility is when, now you see this cannot be 0 because it is 0 at z equal to infinity. This cannot be 0. Why? Because y varies from 0 to b, and for all in this range sine ky can take any values. This cannot be 0 because if this is 0, the equation will be 0 for all x and y, which is not possible. So only possibility is when sine kxa equal to 0 implies kxa is equal to m pi, or kx is equal to m pi by a, where m is equal to 1, 2, 3, etc. So this is the next important equation. Okay. So finally, you can write the equation A2 implies A2 is equal to EZS is equal to E0. So A2 is this one, E0. We already found the expression for kx and ky. You substitute the values for that. So Ez is equal to E0 sine kx is m pi by a. This is multiplied by x because it is kx into x multiplied by sine ky, which is n pi by b multiplied by y. This is ky into y multiplied by y e raised to minus gamma z. And this is the single most important equation in the waveguide. Okay, because we have found out an expression for EZS, which is coming in our EXS, EYS in terms of the length and breadth of the waveguide. So the length and breadth or the dimensions of the waveguide has a huge influence on the electric field component along the direction of propagation. Okay, so we have found out an expression of EZS. And remember that we are using transverse magnetic wave. And for transverse magnetic wave, H said S is equal to 0. This you should keep in mind. Okay. And this M and N are called as modes of the wave. And we usually represent it as Tm, small letter m, small letter n. And m can take value from 0, 1 to etc. N can take value 0, 1 to etc. So this can be like Tm 0, 0, Tm 0, 1, Tm 1, 0, Tm 1, 1, Tm 2, 0, Tm 2, 1, etc. etc. And we will see that, so these are called the modes of propagation. Modes of propagation of TM wave. So if we have time, I'll also try to demonstrate how this modes looks like inside a waveguide. Okay, fine. Now what we are going to do is we have found EZS, but that doesn't complete things, because we need to substitute EZS in our equations A, B, C, D. Okay, for a TM wave, H said is 0, which means this is 0, this is 0, this is 0, and this is 0. And you substitute EZS in this expression from the equation. Let me number that. I think I have numbered this. From the equation number, let's say A dash. So substitute A dash in A, B, C, D, and also applying H ZS is equal to 0 for TM wave, we get. So I'm going to substitute EZS in the equation starting in this one. Okay, here I am going to substitute EZS, and I am going to make H ZS equal to 0, which is this is 0, this is 0, this is 0, this is 0. I'm just substituting the value of EZS. So if you substitute this value of EZS, you will end up getting, I'm not going to make derivation at all. You can write yourself. EZS is equal to minus gamma by h square m pi by a into E0 cos m pi x by a sine n pi y by b e raised to minus gamma z. E ys is equal to minus gamma by h square n pi y b E0 sine m pi x by a into cos n pi y by b e raised to minus gamma z. Hxs is equal to j omega epsilon by h square n pi by b E0 sine m pi x by a cos n pi y by b e raised to minus gamma z. Hys is equal to minus j omega epsilon by h square m pi by a E0 cos m pi x by a sine n pi y by b e raised to minus gamma z. This is the equations of electric and magnetic fields for transverse magnetic wave inside a rectangular waveguide. Okay, these are very important equations. Fine. Then we have a term called H. We have already stated previously in the previous class that, let me see where I have stated that. You see that H square is equal to gamma square plus omega square mu epsilon, or it is equal to kx square plus ky square. Okay, and we have found out the value for kx and ky, which is this and this. So the value of h square is equal to kx square plus ky square, that is m pi by a whole square plus n pi by b the whole square. This is also important. Okay, and we have already told that h square is also is equal to gamma square plus omega square mu epsilon. This we have already told. Okay, so if you let us just equate both equations, because both are h square, equating both equations, you have gamma square plus omega square mu epsilon is equal to m pi by a whole square plus n pi by b whole square. So you have gamma square is equal to m pi by a whole square plus n pi by b whole square minus omega square mu epsilon. Okay, or gamma is equal to square root of m pi by a whole square plus n pi by b whole square minus omega square epsilon. This is another equation. Now we are going to look at what are the possible values of m and n for which you have a wave inside a waveguide. We will see that there are some values for m and n for which there won't be any wave, and for some values of m and n there is a wave. Okay, so we are going to find out what are all the values of m and n for which you have a wave inside a rectangular waveguide. Okay, so this gamma is actually the propagation constant, which we have already seen. Which is equal to alpha plus j beta, where alpha is the attenuation constant, beta is the phase constant. Okay. Now let m pi by a whole square plus n pi by b whole square is greater than omega square mu epsilon. Remember, our equation of E at any point is some constant E0 e raised to minus gamma z e raised to j omega t. This is our equation. Okay. Now this is E0 e raised to minus alpha into e raised to minus j beta e raised to j omega t. This is equal to E0 e raised to alpha cos of, if we take the real part, omega t minus beta z. This is alpha z, sorry. Okay. Remember this one. Now you see that if beta is equal to 0, you will not have this cos term, which means it is some exponentially decreasing function. It is not a wave. Okay. Let's complete this. So let m pi by a whole square plus n pi by b whole square is greater than omega square mu epsilon. Implies your value of gamma is real, right? If you substitute it here, you see this is positive. So the value of gamma is positive. So the value of gamma is real. Value of gamma is real implies gamma is equal to alpha plus j beta. Real implies is equal to alpha, or beta is equal to 0. When beta is equal to 0, E is equal to E0 e raised to minus alpha z into e raised to j omega t. So this is E0 e raised to minus alpha z cos of omega t. Now you see that the wave now doesn't depend on the space. Z. Which means this wave cannot propagate. Or you can say this is not an EM wave. Okay? Because there is no phase shift in the space variable Z. Implies at m pi by a whole square plus n pi by b whole square greater than omega square mu epsilon, there is no wave motion inside rectangular wave. So this is for TM. This is a very important result. So what is the argument? We argue that for a wave to propagate, there should be a space variable which changes with space z or some other x or y. When m pi by a whole square plus n pi by whole square is greater than omega square mu epsilon, there is no space variable in the equation, because of which, although there is cos omega t, it varies only with the time, but our EM wave should vary both with time and space. Since there is no space variable, this wave cannot propagate inside a wave, right? Or you can say there is no wave motion in this condition. So wave motion will occur only when m pi by a whole square plus n pi by b whole square is less than omega square mu epsilon. So at this condition, the value of gamma is complex, because you see when you substitute, when you have this value less than this value, this is a negative value. Root of negative value is j times some real value. So only in this condition that the wave of wave motion will occur. Or there is a cutoff condition, which is m pi by a whole square plus n pi by b whole square is equal to omega square mu epsilon. This is the cut-off condition. So if it is equal to, this is a cut-off condition, the wave can occur or might not. If it is less than, then the wave will not occur. Sorry, wave will occur. And if it is greater than, the wave will not occur. So you see, omega is actually 2 pi f. This is 2 pi f whole square. So we can reduce something called as a cutoff frequency. So let's do that. So you say 2 pi f whole square mu epsilon is equal to m pi by a whole square plus n pi by b whole square. Let's bring mu epsilon to the right hand side, and you have 4 pi f square here, 4 pi square f square here. So let's all bring to the left hand side. So f square is equal to 1 by 4 pi square mu epsilon into m pi by a whole square plus n pi by b whole square. Or f is equal to, take the square root of the whole thing. So 1 by 2 pi root over mu epsilon into square root of m pi by a whole square plus n pi by b whole square. Okay, and this is called as the cutoff frequency of TM wave in rectangular waveguide. So all the waves which have frequency above Fc will propagate inside the waveguide. Okay, so if F is greater than Fc, TM wave will propagate inside rectangular waveguide. If F is less than Fc, no wave motion. So this is called as the cutoff frequency. It's kind of like a high pass filter. Okay, fine. So I think our time is up. I have some more to, I thought I will complete that, but anyway, we will continue this in the next class. Okay, I hope you have understood this because it's a pretty important topic, and during the semester exam, they have always asked at least one derivation from either TM or T modes. Okay, fine. So let me check the attendance. Okay, just a second. So 1 is absent, 2 absent, 3 absent,
4.
4, okay.
5.
വിളിക്കണ്ട. I will just let you know who all absent is. അവര് ഞാൻ വിളിക്കുന്ന നമ്പർ ആരെങ്കിലും പ്രസന്റ് ആണെങ്കിൽ പറഞ്ഞാൽ മതി. Okay, 9 absent, 15 absent.
Sir, 15.
15 ഉണ്ടോ? Okay. Fine. പിന്നെ 21 absent, 24 absent, 26 absent, 34 absent, 38 absent, 42 absent, 45 absent, 46 absent, 47 absent, 48 absent, and 49 absent. 56 absent and 58 absent. Okay. Now, absent number 1, 2, 3, 9, 21, 24, 26, 34, 38, 42, 45, 46, 47, 48, 49, 56, 58. Okay. 12 present. Fine. Okay. So we'll meet again on day after tomorrow. So thank you for listening.